Hello, hello, hello. Welcome back. Here we are in Unit 3, Absolute Value. We are in Section 3.2, which we are going to be graphing the absolute value function. So, remember absolute value, the definition of it is just the distance of a number from 0. So we know that the absolute value of 3 is really saying how far away is 3 from 0, and we know that that is 3. The absolute value of negative 2 is literally meaning how far is negative 2 from 0, and that is 2 units, 0 units. When it comes to the last problem, the absolute value of negative 2 minus 3, well, what is negative 2 minus 3? It's negative 5. And so what is that? It's 5. So you know this, you should be familiar with this. So we are going to be looking at our absolute value parent function. F of x is equal to the absolute value of x. That is our parent function. And then we're going to add all these different transformations to it to get these new absolute value graphs. So what I want to do is I want to create a table with some points and then plot that so we see what our parent function looks like. I'll do negative 3, negative 2, negative 1, 0, 1, 2, and 3. So if I'm plugging in x, those values of x, into this function, remember y is our f of x. The absolute value of negative 3 is 3. The absolute value of negative 2 is 2. Absolute value of negative 1 is 1. And then we would have 0, 1, 2, 3, so on and so forth. So if I plot those points, I'm going to get a picture of my parent function, the absolute value parent function. And I know that you have all seen this graph before. It looks like a V. Its vertex is at the point 0, 0. And so what I want to do as we are observing this function is I want to list out some of its characteristics. Remember, we're cycling in some previous information from Unit 1, all those characteristics. So domain, range, intervals where the graph is increasing, decreasing, positive, negative, etc., etc. Domain, remember, those are x values from left to right. What are being used? For this, it would be negative infinity to positive infinity. Range is from bottom to top, listing out the y values used. And so here, the lowest y value is 0, and it is included, and then all the way up to infinity. Where is this graph increasing? So remember, we're writing an interval, so we're using the x values of where this graph is going up from left to right. So starting at 0, going all the way to infinity, my graph is increasing. Remember, increasing and decreasing are always going to use parentheses when we're writing those intervals out. Remember, you can think of it kind of like a roller coaster. When I'm at 0, I'm not really increasing, but the millisecond I get off of 0 and I start going towards infinity, I am increasing. Same thing for decreasing, so we're going from negative infinity all the way to 0. Just in case I were to ask you, remember positive and negative intervals. So if I was asking for the positive interval here, it would be from negative infinity all the way to 0, and then from 0 to infinity. I cannot include that x value of 0 because when x is 0, y is 0, and 0 is not positive nor is it negative. So I cannot include it in that interval. Extrema is the next characteristic that we want to list. Extrema might be a new word for you. In Unit 1, we talked about an absolute or a global maximum and minimum on a graph. And so that is part of what extrema is. We have the absolute or the global maximum and minimums. We also have something called relative or local maximum and minimums. And so just like absolute and global mean the same thing, local and relative are going to mean the same thing, but we're not going to talk about those just yet. We're only going to be talking about our absolute or our globals. And so for this particular graph, we do have that absolute or that global minimum. And it is at our vertex. It is at 0, 0. It's our vertex. Okay, so remember with absolute and global mins and maxes, I might ask you the location or the value of it. Remember, location is x, value is y. Location, value. Okay. And then in behavior, remember we write that as x approaches infinity, y was approaching, and then x approaches negative infinity, y is approaching. So for this case, our y's are approaching infinity in both directions. And then the last one is something new, but I'm sure you've heard of it before, and that's symmetry. Does this graph have symmetry? Is it symmetric? Absolutely. What is its line of symmetry? That would be the y-axis. Okay, you can see here, if I cut it or fold it along that line, it would be the same on both sides. Let's remember that later on. Okay, going to our box here, we're going to list out our transformations again. Remember, any transformation that's listed or noticed inside of the parentheses, that is going to be horizontal. So maybe a shift right, shift left, horizontal stretch, horizontal compression, or maybe a reflection over the y-axis because I'm flipping from left to right or right to left. So all of those are occurring inside the parentheses. If it's outside of the parentheses, that's going to be your vertical transformations. So shifting up, down, vertical stretch, vertical compression, or a reflection over the x-axis, going from top to bottom or bottom to top. So the description, this should not be anything new. We did this in the previous section. So if I see x minus 8 inside the parentheses, I am shifting what direction? Right, good job. X plus h would be a shift left. Remember, it's opposite of what you think. If I see some number inside of the parentheses being multiplied to x, two things could happen. That number could be between 0 and 1, or that number could be bigger than 1. If the number is between 0 and 1, it's going to be a horizontal stretch. So that might be 1/2, 1/3, 2/3, whatever. If that number is bigger than 1, let's say it's 2 or 2.5 or 5, then that's going to be a horizontal compression because, again, remember, it's the opposite of what we think because we're dividing by that number. When I divide by a number bigger than 1, I get smaller. When I divide by a number smaller than 1, I get bigger. And then the last thing is when I see that negative on the inside, I know I am reflecting over that y-axis. Oops. So what does that look like for us in the absolute value graph? Or absolute value equation, excuse me. So I'm just going to replace my parentheses with an absolute value. And that's it. This is what it's going to look like. Absolute value of x plus some number. For these, it's going to look like f of x equals absolute value of some number times x. Here, it would look like f of x is equal to negative x. We know, okay, you might be thinking, well, the absolute value, the negative of any number is always going to be positive. That's right. We know that the absolute value of negative x is the same thing as the absolute value of x. That's why I said, remember that symmetry. This parent function has y-axis symmetry. So if I reflect over the y-axis, it's not going to change my graph. It's going to look the exact same, which is why this is happening here. Okay, that's one of the properties. And then, of course, on the right-hand side, everything is happening on the outside of the parentheses, so that's all our vertical transformations. Those are pretty straightforward. Those are what you think. So when you see a plus k on the outside, that means we're shifting up. When you see a minus k, we're shifting down. When you see a number multiplied in front, again, two things could happen. It could be between 0 and 1, or it could be bigger than 1. This time, if it's between 0 and 1, it will be a vertical compression, okay, because we multiply by that number. So if I multiply by a number smaller than 1, I get smaller. And then here would be a vertical stretch, because if I multiply by a number bigger than 1, I get bigger. And then lastly, that is going to be a reflection over the x-axis. So again, what does that look like for us in the absolute value equation? F of x is equal to the absolute value of x plus some number. F of x is equal to the absolute value of x minus some number. F of x is equal to some number times the absolute value of x. And then f of x is equal to negative absolute value of x. Okay. So really quick at the bottom, I kind of call this my skeleton, what it's going to look like in that absolute value equation. And so if we are taking our parent function and we shift it left, right, up, or down, that is going to be the location of that new vertex. So our vertex is going to be wherever h and k are. So if I've shifted right 1 and up 3, then my new vertex is 1, 3. If I shift left 2, down 1, then my new vertex is negative 2, negative 1. Okay? So that's what we're going to do right now. We are going to see an absolute value equation with transformations. We are going to list what those transformations are, find the new vertex, plot it, state the domain and range, sketch that graph. So here we go. Let's see. So the first thing I see is I see x minus 2 inside the absolute value. So I know that that is going to the right 2. And then I see a negative 3 on the outside. So I know I'm going down 3. So that means my new vertex is 2, negative 3, which is right here. From that point, I want to continue my function. What we didn't talk about here is a pattern that we see. Notice for this function, our slope is a positive 1 and a negative 1. I'm going from my vertex, I'm going right 1, up 1, right 1, up 1, right 1, up 1, left 1, up 1, left 1, up 1, left 1, up 1. Over and over and over again. That doesn't change unless I have some kind of vertical stretch or compression or horizontal stretch or compression. So that pattern is going to remain the same. Even though I've shifted it to the right and down, I'm still going to go right 1, up 1. Oops. Right 1, up 1, right 1, up 1, right 1, up 1, left 1, up 1, left 1, up 1. And so we get that V-shaped graph. And there we go. Domain here is negative infinity to positive infinity. Range from bottom to top. Start from the bottom. Now we're here. We think of Drake, right? Lowest y value is a negative 3, which is included, going all the way up to that positive infinity. For the second graph, so I see a negative in front. So I know immediately that is a reflection over the x-axis. Okay, because it's vertical, so going from top to bottom, bottom to top. And then I also see on the outside that I'm going up 2 units. So my vertex is only based on the shift. So if I'm only going up 2 units, then I know my new vertex is at 0, 2, right here. Because I have reflected over the x-axis, instead of going right 1, up 1, I'm now going to be going right 1, down 1. And then instead of going left 1, up 1, I'll go left 1, down 1. I don't have any vertical stretches or compressions. I don't have any horizontal stretches or compressions. So that slope remains the same on both sides, other than the fact that we made it negative because there has been a flip. If I reflect over the x-axis, my graph should now be opening downward, which it is. Domain here is actually still negative infinity to positive infinity, but now our range from bottom to top is negative infinity to 2, including that 2. Let's try some more. So here I see a 2 in front, so that means that I have a vertical stretch. So I'm going to be getting twice as tall, if you want to kind of think of it that way. And then I also see a negative 1 on the inside of the absolute value, so that means I'm going to the right 1 unit. So that is my new vertex, 0, 1, right here. So with that vertical stretch of 2, instead of going right 1, up 1, my ups are going to be multiplied by 2. So right 1, up 2, right 1, up 2, right 1, up 2. That is my new slope. Those vertical stretches or compressions are going to be acting as your slope in an absolute value equation. Domain, again, negative infinity to positive infinity. Wonder. Domain here was negative infinity to positive infinity. Domain for A and for B were negative infinity to positive infinity. So was C. I wonder if that's a pattern. Okay, range bottom to top, 0 to infinity. Now we're adding on in behavior. So as x approaches positive infinity, y is approaching positive. As x is approaching negative infinity, y is still approaching positive. For absolute value equations and in behavior, both sides will always be going in the same direction. So they're either both going to be going up or they're both going to be going down. Okay, let's do it one more time. So here I see I see 1, 2, 3. I see 4 transformations. I see a negative in front, so that means I'm reflecting over the x-axis. So my graph is going to be opening downward. I also see a 3/4 in front, so that is going to be a vertical compression because that's a number less than 1, so it's going to get shorter per se. Inside those absolute values, I see x plus 1, so that means I'm going left 1. And then on the outside, I see that -2, so that means I'm going down 2. So, of course, that is my new vertex, -1, -2, which is right here. I know I'm reflecting over the x-axis, so instead of going right and up, I will go right and down. Instead of going left up, I'll go left down. Instead of going right 1, down 1, I'm going to be going really right 1, down 3/4 of the way. Well, instead of me estimating where that is, I know that that 3/4 is acting as my slope. So I can really just go down 3, right 4. 1, 2, 3, 4. Down 3, right 1, 2, 3, 4. And so then I get those 2 points on the line to make my life a little bit easier. And now I have that absolute value graph that has been reflected, vertically compressed, shifted left, shifted down. Domain, you could probably bet money now, negative infinity to positive infinity. Our domain for any absolute value function is always going to be negative infinity to positive infinity, no matter what. No matter how you flip it, shift it, compress it, stretch it, it's always going to be that. Range for this one, bottom to top, negative infinity all the way up to -2, including that value. In behavior again, as x approaches infinity, y is approaching negative infinity. As x approaches negative infinity, y is approaching negative infinity as well. Okay, those should be pretty easy for you. Absolute value properties, you probably already know some of these. Obviously, the first one you should already know. The absolute value of any number is going to be greater than or equal to 0 because of that definition. Absolute value is a distance from 0. Distance cannot be negative. Distance can be 0. So absolute value of anything is always going to be greater than or equal to 0. We already know that the absolute value of a negative number is the same thing as the absolute value of that positive number. The last two, you should know, maybe you don't, maybe you just forgot. If I am multiplying two things within the absolute value, it is the same thing as taking the absolute value of each of them separately and then multiplying them together. And then same thing for division. The absolute value of A divided by B is the same thing as the absolute value of A divided by the absolute value of B. Granted that B is not equal to 0 because we cannot divide by 0. Okay, those last two, really the third one comes into play the most often for us. So this is probably the one that we will use the most. It's the most beneficial for us. So I'm going to be applying that in E and F here. Remember I said in 3.1, the way that I graph these horizontal transformations is I factor out that B value first. So what I see here is I have to factor out a 2, which is going to leave me with x minus 1 inside the absolute values. Well, inside my absolute value, I am multiplying two things. I am multiplying 2 to x minus 1. Well, based on this third property, that means I can really write it as the absolute value of 2 times the absolute value of x minus 1. Well, I know the absolute value of 2 is 2. I do not know the absolute value of x minus 1, so I leave it. So this is kind of what I'm going to be going off of. Oops. But even so, in the original function, what transformations do I have? I had a number inside of the absolute value that was bigger than 1. So that's a horizontal compression. Even though our properties took it here, which now makes it look like a vertical stretch. That's okay. For absolute value functions, a vertical stretch is the same thing as a horizontal compression and vice versa. Only for absolute value functions though, because it's based on that slope. And then of course we're going to the right 1 unit. So because of that shift, I know my vertex is now 1, 0. That horizontal compression, which is also acting as my vertical stretch, is my slope, right 1 up 2, right 1 up 2. And there you go. Oh, that was not good. Okay, domain, we already know, negative infinity to positive infinity, range 0 to infinity. Let's try it one more time. 2/5 in front, absolute value of negative x plus 2 minus 1. So 2/5, absolute value of negative x minus 2 minus 1. Using that property, this is really the same thing as the absolute value, 2/5, absolute value of negative 1 times absolute value of x minus 2 minus 1. But what is the absolute value of negative 1? It's 1. So really I have 2/5 times 1 times the absolute value of x minus 2 minus 1. I don't need this. Multiplying by 1 doesn't change anything. All right? So don't put it. Don't put it. All right? So I can get rid of this completely. And I just have this now. And so if I list out those transformations, really I had a vertical compression. I really had a reflection over the y-axis, but we know what happens when I reflect over the y-axis. Nothing. That's my line of symmetry. When I reflect over the y-axis, it doesn't even look like I changed my graph. That's why we could get rid of it. Okay? And then I know I'm going to the right 2 and down 1. That right 2 down 1 is my new vertex. That vertical compression is now my new slope. Rise 2, oops, right here. Rise 2, run 1, 2, 3, 4, 5. Rise 2, run 1, 2, 3, 4, 5. That vertical compression looks like a horizontal stretch. Domain, range. Okay. And so now that I have given you the transformations and you draw the graph, I want to go the other way around. So if I give you the graph, could you write the transformations and write that function? So what I want to do is I want to start with where my vertex is. So in this problem, my vertex is at 3, negative 2. So that means I went right 3, down 2. So that means I need to see something like this. I also need to check to see if there's any kind of stretches or compressions. So to do that, I check my slope. I see that my slope is a positive 2. I went right 1 up 2, left 1 up 2. So that means I have a vertical stretch of 2. You know that you really could write this like this as well, but please do not get caught up in that. Please just write it how you see it. Go with your shifts and then check your slope. Okay, let's go ahead and do this one first. So my vertex is at 1, 3. So that means I've shifted to the right 1 and up 3. So I know that I need to see something like this. And then there again, I need to check my slope. I notice that my slope is 1, but my graph is not opening upward, it's opening downward. So that means I had to have a reflection over the x-axis. So that means I had to have a negative in front. So this is really f of x equals negative x, absolute value of x minus 1 plus 3. And then this would be f of x equals 2 times absolute value of x minus 3 minus 2. So that's the first part. The second part says I need to sketch the inverse on that same graph. So remember, for inverse, it's a 2-step process. The first step is switching the x and y, and the second step is solving for y. That's to find the inverse of a function. To graph an inverse, I just need to do that first step. I just need to switch the x and y coordinate and then graph it, okay? So I'm going to do that. I'm going to pick some points on my original function, switch the x and y, and then plot that new point. So if I had a vertex at 3, negative 2, then I switch that around, and now I have a vertex at negative 2, 3. If I had a point at 4, 0, then now I have a point at 0, 4. If I had a point at 2, 0, now I have it at 0, 2, etc., etc. So here is my inverse, f to the negative 1 of x. Remember that inverse function notation. Same thing for the second graph. My vertex was at 1, 3, so now my new vertex is going to be 3, 1. It is a point on the original graph. That is okay. I see that I have a point at 2, 2. I swap that around. It's still 2, 2. I see that I have a point at 0, 2, 2, 0. I see that I have a point at 4, 0, 0, 4. Here's my new graph. Or here's my inverse, excuse me. So this is my inverse. All right. And then the last section. So it says, write the equation of an absolute value graph with the transformations listed. So we are listing the transformations, and then you are writing the function based on that. So the first one says it's been shifted to the right 3, reflected over the x-axis, followed by a vertical shift up 2. So if I shift to the right 3, that's going to look like x minus 3 inside of the absolute value. If I reflect over the x-axis, that means I have a negative in front. If I shift up 2 units, then that means I have a plus 2 at the end. So this is my function. Okay. Then it says I shift left 2, shift up 4, followed by a vertical stretch by a factor of 2. Well, if I shift left 2, that's going to be x plus 2. If I shift up 4, that's going to be a plus 4. If all of this is followed by a vertical stretch by a factor of 2, then that means all of this gets multiplied by 2, which then translates to 2 times absolute value of x plus 2 plus 8. Remember, with vertical transformations, you have to follow PEMDAS order. So because I didn't multiply my vertical stretch first and then shift up, then I need to distribute that vertical stretch to everybody. So if I go up 4 and then I vertically stretch, I didn't just go up 4, I actually went up 8. Okay, so this is actually your new function, or your function. And then the last one, it says a horizontal compression by a factor of 1/2. Be careful there. Remember, horizontal compressions and stretches are... Horizontal compressions and stretches are the opposite of what you think because you're dividing by that number. So if you saw something like this is actually a compression because I'm dividing by 2, which is actually the same thing as multiplying by 1/2. If I saw this is actually a stretch because dividing by 1/2 is the same thing as multiplying by 2. So because I see compression here, I want to see a number bigger than 1. So because it's 1/2 here, I know that I need to use the reciprocal. And so I do have 2x. If that would have been a 1/3, then it would have been 3x, etc. Use the reciprocal. Okay, so then I have followed by a shift down 2. So I can just take that and then go down 2. And that is my function. All right. That's it. See you later.